Good evening. Good evening, everyone. This is the problem solving session, week 7 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder, Department of Chemical Engineering, IIT Guwahati. While this live session is handled by myself, Ankara Kartika, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, this is our week 7. The session happens every Friday between 6 p.m. and 8 p.m. So we'll start the session now. I hope I am audible, just for confirmation. Yeah. So basically, in this course, this is a 12-week course. So till now we have seen about fluidized beds, its advantages, disadvantages, and solid classification and various phenomena. For example, in week 1 to 2 we have covered the introduction to the fluidization, its advantage and disadvantages while using fluidized beds and industrial application of fluidized beds, followed by characteristics of solids, classification of solids, flow characteristics and its outline in different types of fluidization. Followed by that, we have seen the flow pattern inside the fluidization system. For example, the flow pattern transition, flow pattern map, frictional pressure drop and its model to analyze, and how solids moves and mixing and segregation that happens within the fluidized bed. And then in week 6 we saw about the gas distribution system. For example, we have seen about perforated plate or porous plate distributor or nozzle type, Stewart type distributor. We have seen various gas distributor types in the fluidized bed and the design for them. And in week 7 the coverage was about bubbling fluidized beds, gas dispersion, gas interchange in bubbling beds, mixing characteristics. And week 8 it is about entrainment and elucidation from fluidized beds. In week 9 we would be dealing with attrition mechanism and its analysis. And week 10 to 11 the focus would be on mass transfer phenomena happening inside the fluidized bed and the various models available to study the same. And in the last week they would be dealing with the heat transfer phenomena and design of the fluidized bed reactors. So in the reference books for the courses, the first one is Cooney and Levenspil's Fluidization Engineering. It is a very good book to cover all the basic aspects of fluidization engineering. Followed by that, we have Gidaspo's Multiphase Flow and Fluidization, Continuum and Kinetic Theory Description. So in this book, we can study the phenomena happening inside the fluidized bed with major focus on the modeling aspects of the fluidized bed also. For example, here we see about the continuum mechanism of the fluid. We assume the solids to behave as a continuum model. Like we have continuum theory for gases, kinetic theory for gases, where we assume the smaller gas particles to be at a certain distance and how fast they move. Similar to that, we make assumption for the solid particles and assume it to behave as a continuum rather than as discrete particles, so that it would ease the in the modeling aspects. And third, we have Giblaris fluidization dynamics. And in last, we have Professor S.K. Majumder's hydrodynamics and transport processes of inverse bubbly flow, first edition. So these are the books and references. These are the course layout and books references are told again just for you people to have a quick recap, and it would be helpful for those who are joining new in this class today. So in today's class we would be dealing mostly with bubbling fluidized beds and its modeling aspects. So how bubbles form inside the bubbling fluidized bed, and what are all the aspects that would influence the bubbling fluidized beds, and so on. For example, in bubbling fluidized bed, there are various aspects which would be influencing the bubbling bubble formation, and the stability of bubbles are also governed by various factors. So the main focus in this week's lecture was about the stability of the bubbles, and what are all the factors available to study the stability of the bubbles, and what are all the theory available to analyze the same. So in this week, the problems and the theory associated would also be focusing on the same theory, that is bubble dynamics and the stability of the bubbles in the bubbling fluidized bed. This can be associated with two phase systems like gas solid systems, or it can be in three phase system like gas liquid and solid also. So we'll move on. The first question for today's thing is, just a minute. So the first question for this big session is basically nothing but, what is the unit of turbulent dissipation rate E? It is meter square per second, meter cube per second, meter square per second square, or meter square per second cube. So basically the answer to this problem is option D, that is meter square per second cube. We will see how, or if any of you have the answer for this question, you can always unmute yourself and say. We'll wait for a minute and then we'll discuss the answer. So yeah, the turbulence dissipation rate, that is epsilon or E, is the rate at which turbulence kinetic energy is converted into thermal internal energy. So the SI unit of epsilon is nothing but joules per kg per second. Rate at which turbulent kinetic energy is converted into thermal internal energy. So the unit for the same is, that is unit for turbulent dissipation rate is joules per kg second. So on converting the joules into we can see it like this, joules per kg how can we say it is joules per kg second? Uh, Joules is equal to Newton meter. Newton is nothing but kg meter per second square. Into meter. So basically what does it mean? Joules per kg second. If put it to this form, we have kg equal to kg meter square by second cube. So we have kg meter square per second cube. So on dividing this by the kg second, we have sorry. It is second square. On dividing it by kg second, we have meter square per second cube. So the right answer to this question is option D, that is meter square per second cube. So we'll go on to question 2. In question 2, it is given that the most important force in stabilizing the bubble is dash force. So in fluidized beds, that is in bubbling fluidized beds, bubbles form and the stability of which depends on several factors. So which are the forces that influence the bubbles formation inside the system? Like for example, in this we have options as viscous force, surface tension force, inertial force, or none of the above. In the similar way, you people give the answer first, or just think of the answer even if you don't want to say it, and justify yourself, and then we'll discuss the answer after a minute. So the answer is actually surface tension force, because we'll see how this is. The result shows that surface tension of air liquid interface exerts a huge impact on bubble stability by reducing the surface free energy and increasing the Gibbs surface elasticity. Surface tension may not be the only determinant of bubble stability. So this is taken from a paper by et al. A review on bubble stability in fresh concrete, mechanism and main factors. So although the context is different from what we are learning, this system for our case is fluidized bed, but a recent study by Zeng et al. Shows that on the stability of bubble stability in the fresh concrete, what they observed is that surface tension between the air liquid interface, since it is a concrete, we are dealing with between air and liquid interface, it exerts a huge impact on bubble stability. How does it impact? It reduces the surface free energy and increases the Gibbs free elasticity. So but then so since its surface free energy is reducing, but what they observed is that it may not be the only determinant of bubble stability, but it is one of the factors influencing the bubble stability. So basically the question is, the most important force in stabilizing the bubble is the surface tension force. There are various forces influencing that, but the most important force is the surface tension force. So we'll go to question 3. In question 3, it is asked that if the bubbles are much larger than the micro scale of turbulence, choose a force which can be neglected. Viscous force, surface tension force, inertial force, none of the above. So the question is basically, if the bubbles are larger than the micro scale of turbulence, which of the forces can be neglected? Uh, so try to give a proper justification for this question and we'll deal with the answers. So the answer is viscous force, because when the bubbles are very larger, the turbulence happens at a very smaller scales, right? So when bubbles are larger, we can neglect the viscous force, because since surface tension plays a very major role, and also inertial force cannot be neglected at that scale. So the only force which can be neglected when the bubbles are larger than the microscale of turbulence is that we can neglect the viscous force, because at that scale it would not be playing a very prominent role, very significant role would not be played by that. So we can neglect it, the viscous force. Even if we neglect it, it would not be affecting significantly the other significantly the bubble formations. So we'll go on to question 4. In question 4, it is asked that centrifugal force can also disintegrate the bubbles as it increases with an increase in bubble size. The bubble breaks up when the centrifugal force is dash the surface tension force, especially at a high pressures when gas density is high. So what the question asks is that centrifugal force can disintegrate. When bubble formation occurs, centrifugal force also plays a major role. At one stage, centrifugal force influences the bubble disintegration because it increases with increase in bubble size, right? When the bubble sizes has been increased, when the bubble size is increased, the centrifugal force would also be increasing, because the diameter of the bubble or the circle is increasing. So at one point, if the bubble size is very less, centrifugal force would be very high. So it disintegrates the bubble. The bubble breaks up when centrifugal force is dash the surface tension force, especially at high pressures when gas density is high. So the answer is option A is less than, option B is more than, option C is equal to, option D is none of the above. So basically the answer is when the centrifugal force is greater than the surface tension force, or it is option B, more than. Because if the surface tension, we have already seen in the previous question what influences the stability of the bubbles. It is nothing but the surface tension force. So at some point, if the centrifugal force is higher than the surface tension force, this surface tension force is, what does it mean? The surface tension force is lowered. So at that point, the bubble disintegrates or the bubble breaks. So the answer is more than the surface tension force. That is, centrifugal force is more than the surface tension force. Then it means that the bubble disintegration can occur. More than the surface tension force, especially at higher pressures when gas density is high. So this is question 4. We'll go on to question 5. In question 5, it is asked that according to Ojima et al. 2015 model, what will be the coalescence time in slurry fluidized bed? Coalescence time is independent of slurry concentration. Coalescence time increases as the slurry concentration increases. Coalescence time decreases as the slurry concentration increases. None of the above. This question is, what will be the coalescence time for the bubbles in the according to the Ojima et al model, that is 2015 model. How the coalescence time would be depending on the slurry concentration, whether it is directly proportional, indirectly proportional, or it is not at all influencing that same. Think about it, we'll answer it in a minute. Like, for all the questions, let us just take a 1 minute break. You people devise the answer in your mind, and then we can discuss it, and then we can come up with an answer. So the answer to this question is, coalescence time decreases as the slurry concentration increases. If the slurry concentration is more inside the bed, in the slurry fluidized bed, what happens is that the bubbles would be formed more frequently, thereby the coalescence time for the bubbles would be reduced. So the coalescence time then would be decreased because the slurry concentration is very high, so that coalescence time is found to decrease. For example, the time Tc elapsed from the bubble contact to the rupture of the liquid film between two bubbles in a quasi two-dimensional column was measured to investigate the effects of the particle diameter on bubble coalescence. This is the Ojima et al. Model. Tc decreases, in other words, bubble coalescence is enhanced with decreasing particle diameter, which results in the reduction of gas holdup or the slurry bubble column. That interaction time between bubble interfaces and particles in the bubble coalescence process after bubble contact is a local phenomenon and rarely depends on the macroscopic behavior of the interface. So what does it mean is that Tc, let us consider Tc is the contact time, that is the time between contact of the two bubbles to the rupture of the, if two bubbles come in contact, what happens is that the interface between the two bubbles ruptures in a two-dimensional column. It was measured, that is the time elapsed from when two bubbles come in contact and then the interface ruptures between the liquid film between the two bubbles. The time elapsed between these two processes is calculated as Tc. It is measured to investigate the effects of the particle diameter on bubble coalescence. That is, the particle diameter in the system's effect was analyzed uh, to be in the how it influences the study of coalescence of the bubbles in the slurry fluidized bed was analyzed. It was found that Tc, that is the time decreases. What happens if the time decreases between two bubbles coming in contact and the rupture of the liquid film? If it decreases, it is known to enhances the bubble coalescence. It is enhanced with decreasing the particle diameter, which results in the reduction of gas holdup of the slurry bubble column. In other words, this interaction between the bubble interface and particles in a bubble coalescence process after the bubble contact is a local phenomenon. It rarely depends on the macroscopic behavior of the interface. So if, what does it mean here is that if particle diameter is decreased, so concentration in general will be more than when compared to the larger diameter particles. If larger diameter particles is there, the time between the bubble contact and the rupture of the film would be very large, so that the sorry, if the particle diameter is reduced or the slurry concentration is reduced, slurry concentration would be reduced. So in such cases, the bubble coalescence is enhanced. Or how can we say that the bubble coalescence is increased when the particle diameter is reduced or the slurry concentration is reduced. So in on contrary to this, when the bubble diameter or the particle diameter or the slurry concentration is more, bubble coalescence is decreased. Consider a very large diameter particle. If the concentration is more, the chances of two particles coming in contact with each other and then the rupture of the film between those two bubbles is found to increase. So if TCE is decreased, what does it mean? The two bubbles coming in contact with each other and rupturing is increased. Bubble coalescence happens very fast. That is, it happens in a short duration of time. So bubble coalescence is enhanced. When does it get enhanced? When the particle diameter is decreased or the slurry concentration is decreased. Uh, the coalescence time decreases as the slurry concentration increases. Sorry for the confusion, actually. I think I've confused you all people. Just forget it, I'll just explain once more. Coalescence time decreases as the slurry concentration increases or the particle diameter decreases. Let us keep Tc is the coalescence time. Two bubbles come in contact with each other and the in between liquid film gets ruptured. So at that point the bubbles coalesce. So the time taken between the particles coming in contact and the particle in between film getting ruptured is known as Tc. So if for example two phenomenon happens, if slurry concentration is more, what does it mean? The concentration is very more, so the particle packing is the particle diameter is less, right? So the packing fraction would be more in that case. The slurry concentration, if it is increased or the particle diameter is decreased, what happens? The chances of two particles, the bubbles coming in contact with each other and the rupture of bubbles is increased in that time. So if the contact chances of contact is getting increased, what happens? The coalescence time gets reduced. That is, coalescence time decreases when the slurry concentration is more or the particle diameter is less. I hope this is clear. We'll go on to question 6. If there is any doubt, please feel free to ask. Since there was a confusion in this question, we'll just take a minute to understand this and then come back. So actually we'll just have a quickly go through this. The thing is, when the particle size decreases or the slurry concentration increases, the chances of the bubbles coming in contact with them with each other is increased. So then the rupture of the film between the bubbles are also increased. The chances for the rupture of film between the bubbles are also increased. Therefore, the coalescence time is decreased. We'll go to question 6. In question 6, it is asked that centrifugal force induced by dash circulation of the gas in a bubble. Internal, external, due to both external and internal, none of the above. Think for a minute, we'll answer this. So centrifugal force in the bubbles, as we all see, how if it increases with increase in the bubble size, and if it is increased beyond the surface tension of the force, surface tension of the bubble gets disintegrated or it gets broken. So how does what induces the centrifugal force inside the bubble is that the internal circulation of the gas that is happening inside the bubble is the one that is inducing the centrifugal force. So the right answer is option A, that is internal circulation of the gas inside the bubble. So we'll go on to question 7. In question 7, in the bubble coalescence model, choose the correct option. The collision of 3 or more bubbles at the same time has a very small probability. Binary collision is normally considered. Both options A and B are correct. Only option A is correct. So, in bubble coalescence model, what is the correct answer? The first option is the collision of 3 or more bubbles at the same time has a very small probability. Binary collision is normally considered, or in option C it is given both A and B are correct, or in option D it is only A which is correct. So the answer is option C, which is both options A and B are correct. What happens is in the bubble coalescence model is that only binary collisions are considered, but at the same time, since only binary collisions of the bubbles are considered, the chances of the probability of the collision of three or more bubbles is very low. So both the options, that is collision of three or more bubbles at the same time, has a very low probability. Binary collision is normally considered. So option C is the right answer. We'll go to question 8. In question 8, it is given that the coalescence of two bubbles in a turbulent flow in the three-phase bubble fluidized bed is usually considered to occur in three steps. So what happens is that the two bubbles which are coming in contact, when they coalesce, there is a theory that is found applicable in the three-phase fluidized bed, which which considers a series of events that occurs in the bubble formation or the bubble coalescence. So what is the correct sequence? The first option is surface of the colliding bubbles flatten against each other, trapping a small amount of liquid between the colliding bubbles. The bubbles collide. So either the option is 1, 2 and 3, or 2, 1 and 3, or 3, 1 and 2, none of the above. So what happens is that consider this okay, this is bubble 1, this is bubble 2. When two bubbles coming in contact, what happens is that they first collide, right? We'll keep this as this. They are colliding against each other. So the options given are surface of the colliding bubbles flatten against each other, trapping a small amount of liquid between the colliding bubbles, or the bubbles collide. So the first option is the bubbles collide. This is the first one. And the second is what happens is that the surface of the colliding bubbles flatten against each other. So they flatten against each other and it looks like this. The surface of the colliding bubbles flatten against each other. So this is second one and this is third one. What happens? We have the flattened surface and they have a small amount of liquid trapped between them. So the right answer is 3, 1 and 2. So option C is the right answer. That is option C, that is 3, 1 and 2. First the bubbles collide against each other and the surface of the colliding bubbles flatten against each other and they trap a small amount of liquid between the colliding bubbles. So just take a minute to analyze the events and then we move on to question 9. So the series of events is that the first bubbles collide against each other and the surface of the bubbles, colliding bubbles, flatten against each other and then they trap a small amount of liquid between the colliding bubbles and then the surface burst out and the coalescence of two bubbles occurs and they grow into a larger bubble. So we'll go to question 9. In question 9, it is given that according to Prince and Blanche, the collision frequency model is defined as uh, how do we define the collision frequency model according to the Prince and Blanche model, that is in 1990. So given theta ij is the collision frequency, theta ijt is the turbulent collision rate, theta ijb is the buoyancy driven collision rate, and theta ijls is the laminar shear collision rate. So the first option A is that theta ij is equal to theta ijt plus theta ijb. Or in option B, it is given that theta ij is equal to theta ijt plus theta ijb plus theta ijls. Option C, it is theta ij is equal to theta ijb plus theta ijls. Or option D, it is theta ij is equal to theta ijt plus theta ijls. So what is given is that how do we define the collision frequency model according to the Prince and Blanche model 1990. Theta ij is the collision frequency model. So how do we come up with the collision frequency model? So the option A, it is given that the collision frequency model is the sum of the turbulent collision rate plus the buoyancy driven collision rate. Or in option B, it is turbulent collision rate, buoyancy driven collision rate, and laminar shear collision rate. Or option C, it is buoyancy driven collision rate or laminar shear collision rate. Option D, it is nothing but turbulent collision rate and buoyancy or laminar shear collision rate. So, what is the correct answer? Just take a minute to analyze the question and give me the answer. So actually, how do we define the collision frequency rate is nothing but we add the sum of the turbulent collision rate, buoyancy driven collision rate, and laminar shear collision rate, because all the three influence the collision frequency. Like how do even the smallest thing that is happening inside the bed influences the collision frequency of the bubbles. So Prince and Blanche model includes the collision frequency from the turbulent collision rate, buoyancy driven collision rate, and laminar shear rate. So bubble coalescence is modeled by considering the bubble collisions due to turbulence, buoyancy, and laminar shear, and by analysis of the collision efficiency of the bubbles. Coalescence efficiency of collisions. Bubble breakup is analyzed in terms of bubble interactions with turbulent eddies. So what happens is that bubble coalescence is modeled by considering bubble collisions due to, like, because of turbulence the bubbles collide with each other, and because of the laminar shear also the bubbles collide with each other, and also the buoyancy force also makes the bubble collide. These factors like turbulence, buoyancy, and laminar shear influence the movement of the bubbles, and thereby um, influencing the bubbles collisions. So all these factors influence the coalescence model. Bubble coalescence is modeled by considering bubble collisions due to turbulence, buoyancy, and laminar shear, and by analysis of the coalescence efficiency of collisions. Bubble breakup is analyzed in terms of bubble interactions with turbulent eddies. So this is from Prince and Blanche 1990 paper. So the reference is also given. You people can take reference from this whenever it is needed. I mean, you can read this paper. It would be interesting for you to go through the paper and come up with the same conclusion. So the bubble coalescence is modeled by considering bubble collisions due to turbulence, buoyancy, and laminar shear force. So all these influence the bubble movement and the collision of the bubbles. So thereby the bubble coalescence is modeled accordingly. So we'll just take a 5 minutes break. We'll meet again at 6:55 and we'll start the session. Uh, Let us all take a 5 minutes break and then resume the session. Thank you. start the session again. I think it is time. In question 10, it is asked that the maximum bubble size as per Liu et al. 1999 model is expressed as Dmax is equal to, approximately equals 2.53 sigma by rho Gg, and option A is that. On option B, it is Dmax is approximately equal to 2.53 into sigma by rho Gg power 2 by 3. Option C, it is Dmax is approximately equal to sigma by rho Gg, or in option D it is sigma option Dmax, that is maximum stable bubble size. According to the Liu et al. Model 1999, it is expressed as 2.53 into sigma by rho Gg power 0.5. So the right answer is 2.53 into sigma by rho Gg power 0.5. In the sigma is the surface tension force, rho G is the density of gas, and G is the acceleration due to gravity, that is 9.1 meter per second square. So the maximum stable bubble size according to Liu et al. Model, that is 1991 model, is nothing but it is expressed as 2.53 into sigma by rho G, sigma divided by rho G into G whole power 0.5, or the root 2. So things to be noted here is that in all these options we have 2.53 except this one, and in this one it is okay, this is the power is not present, and here it is 2 by 3, and here it is 1 by 2, or square root of this. So the answer to this is, we have 2.53 into square root of numerator we have sigma, that is the surface tension, and in denominator we have rho G into G. Rho G is the density of gas and G is the acceleration due to gravity. This is the right formula for finding the maximum stable bubble size. Maximum stable bubble size according to Liu et al. Model, that is in 1999 model. How do we define the maximum stable bubble size? It is nothing but approximately equal to 2.53 times square root of sigma by rho Gg, where rho G is the density of gas and G is the acceleration due to gravity, and sigma is the surface tension. We will see question 11. Okay, in question 11, it is asked that as per Coelho and Tavlerade's 1977 model, which of the following is the correct expression for liquid droplet coalescence rate? Pc is equal to exponential of minus Tc by Ti, and or Pc is equal to exponential of Tc by Ti, or option C is Pc is equal to exponential of minus Tc by 2 times of Ti, or option D, it is none of the above. So this is the liquid droplet coalescence rate for the bed according to the Coelho and Tavlerade's 1977 model. So the right answer is option A, that is Pc is equal to exponential of minus Tc by Ti. So we'll see how. As per Coelho and Tavlerade's model, breakup is caused by collision of drops with turbulent eddies. They postulated that only energies associated with eddies smaller than the droplet diameter will cause breakup. Coalescence rate can be expressed as a product of collision frequency and coalescence efficiency, since not all collision between droplets lead to coalescence event. For coalescence of droplets to occur in a turbulent flow field, the droplets must first collide and then remain in contact for sufficient time so that the process of film drainage, film rupture, and coalescence may occur. During these processes, a turbulent eddy may separate the droplets and prevent coalescence. The force which compresses the drops must act for a sufficient time that intervening films drain to a critical thickness so that the film rupture and coalescence will take place. It becomes obvious that the time for these processes to occur, the contact time must exceed the coalescence time of the droplets. So, what happens is that in according to Coelaglo and Tavleret's 1977 model, what causes the breakup of bubbles is that bubble breakup is caused by collision of droplets with the turbulent eddies. When the droplets collide with the turbulent eddies, the bubble breakup occurs. What they postulated is that only energies associated with eddies smaller than the droplet diameter will cause breakup. For example, consider if the eddies are very larger than the bubble diameter, it would not lead to breakup. Rather, smaller eddies would affect the bubbles and thereby causing the breakup of those bubbles. So the breakup is caused by the bubbles or the droplets coming in contact with the turbulent eddies when these turbulent eddies are smaller than the bubbles. So that the energies associated with the smaller bubbles will cause breakup. Coalescence rate can then be expressed as a product of collision frequency and coalescence efficiency. So coalescence rate is nothing but it is the product of collision frequency and how frequently the bubbles or the eddies come in contact and the coalescence efficiency. Because not all the collisions lead to coalescence event. Between the two droplets, whenever collision occurs, it does not lead to coalescence. Rather, only few collisions lead to coalescence. So, coalescence rate is therefore defined as a product of the collision frequency and the coalescence efficiency. So, for coalescence of droplets to occur in a turbulent flow field, the droplets must first collide and then remain in contact for a sufficient time so that the process of film drainage, film rupture, and coalescence may occur. So this one we saw in all previous thing itself how two bubbles come in contact with each other and their and between them the film is remaining so strong or the straight film is getting formed and after that it gets ruptured and the liquid between gets trapped between the film and then the rupture of film takes place. So not all the collision between the bubbles would lead to coalescence. Rather, they must collide and be in contact with each other for a sufficient time. In that time, the film drainage, film rupture, and coalescence occurs. During these processes, a turbulent eddy may separate the droplets and prevent coalescence. So, if a turbulent eddy is present over there, the chances for it separating the droplets and preventing coalescence are there. The force which compresses the drops must act for a sufficient time. The force which compresses the drops must act for a sufficient time so that the intervening film drains to a critical thickness so that the film rupture. For example, the two bubbles must be in contact for a sufficient time. That is, the contact time is tau and the coalescence time is t. So for if they are in contact for a sufficient time, after that the film rupture and the coalescence will take place. That is time t, that is coalescence time. So in these aspects, what Coelaglo and Tavlarides in 1977 stated is that the breakup of the is caused by collision of drops with turbulent eddies. When turbulent eddies come in contact with the bubbles, they cause bubble breakup. Because when the bubbles are smaller than the eddies, it would not lead to anything. On the other hand, when these eddies are very smaller than the droplet diameter, or the droplet diameter is larger than these eddies would cause the breakup of those bubbles. And then coalescence rate between the bubbles is influenced by the product of collision frequency and the coalescence efficiency, because not all collision leads to coalescence. For the collision to occur, the bubbles must remain in contact with each other first for a very large period of time. In that time, the bubbles must remain in contact with each other and they must form a straight surface. In that, and after that the liquid gets trapped, and then the film drainage, film rupture and coalescence may occur. A turbulent eddy may prevent the coalescence. The force which compresses the drops must act for sufficient time so that the intervening film drains to a critical thickness, so that film rupture and coalescence will take place. Now, the contact time between the bubbles must exceed the coalescence time of the droplets. So we all have the coalescence time T, uh, which the contact time must be more than that coalescence time. For example, let us consider that if the coalescence time for the droplet is 5 seconds, the bubbles must remain in contact for at least 6 seconds. Only then the coalescence between the bubbles would occur. So this is given by exponential of minus t by tau. Here it is given by minus tc by ti. That is the probability of the bubbles coming in contact and colliding and leading to collision. Sorry, coalescence. The question was basically which of the following is correct expression for liquid droplet coalescence rate? It is minus Tc by Ti. The unit of collision frequency between bubbles with diameter di and dj is defined as meter square per second square, meters cube per second cube, 1 by meter cube second, or meter square per second cube. So the collision frequency, we all know it is frequency if it is per second. So the collision frequency between bubbles with di and dj is defined as 1 by meter cube second, because in the formula we have di square plus dj square into di plus dj in some form. So it is meter cube 1 by meter cube in, I mean, per second, 1 by meter cube second. So answer is option C. For slurry column, its statement is correct. Option A, bubble coalescence enhances with decreasing particle diameter, or bubble coalescence reduces with decreasing particle diameter. Bubble coalescence is independent of particle diameter, none of the above. So this was a question we discussed previously also. So just take a minute to understand and analyze the answer, and then we'll discuss it shortly. So bubble coalescence enhance with decreasing the particle diameter. So we have seen exactly the same concept in the previous question. So the right answer is bubble coalescence enhanced with decreasing the particle diameter. So here in previous question itself we have seen that the time elapsed from the bubble contact to the rupture of the liquid film between two bubbles in a quasi two-dimensional column was measured to investigate the effects of the particle diameter on bubble coalescence. TC decreases, in other words, bubble coalescence is enhanced with decreasing the particle diameter, which results in the reduction of the gas holdup of the slurry bubble column. Interaction between bubble interface and particles in bubble coalescence process after bubble contact uh, is a local phenomena, and it rarely depends on the macroscopic behavior of the interface. Coalescence time is decreased as the slurry concentration increases or the particle diameter decreases. So for example, when two bubbles come in contact with each other, the time taken between the contact of the bubble to the rupture of the liquid film between two bubbles is measured as Tc, and it was influenced by the particle diameter, that is particle diameter. So in other words, bubble coalescence is enhanced when it would be enhanced when the Tc is decreased. When Tc is decreased, bubble coalescence is enhanced. When this would happen is that the particle diameter is decreased. When particle diameter is decreased, the chances of two bubbles coming in contact with each other and coalescing is increased. So the bubble coalescence is enhanced with decreasing particle diameter. Therefore, the Tc or the contact time is also decreased. Decrease, in other words, bubble coalescence is enhanced with decreasing particle diameter, which results in the reduction of gas holdup of the slurry bubble column. Reduction of gas holdup is reduced in such cases in the slurry bubble column. So coalescence time decreases as the slurry concentration increases, so the particle diameter decreases. So when particle diameter decreases, coalescence time decreases, so the bubble coalescence phenomenon is enhanced. So the right answer is option A, bubble coalescence is enhanced with decreasing particle diameter. In question 14, it is asked that which of the following statements is true. Bubbles of different sizes have different rise velocities. Bubbles of different sizes have same rise velocity. As per Prince and Blanche, the collision model is a summation of turbulent collision rate, buoyancy driven collision rate, and laminar shear collision rate. And option D, it is both option A and C are right. And which is the right answer? Just think for a minute, because we all know the answer to this question. And a similar one of the concepts we also saw in previous problem. So think and analyze, and you can unmute yourself and answer the question as well. So actually, different bubbles have different rise velocities. We all know the formula for UVR depends on bubble size, that is dP. So option A is right. Bubbles of different sizes have different rise velocities. Also, as per Prince and Blanche model 1919, collision model is the summation of turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate. This we have seen in previous problem actually. Ah, in this we have seen that Prince and Blanche model collision frequency is modeled as the sum of the turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate. So answer is sum of the three. So the right answer in the given question is both option A and C are right. Which is bubbles of different size have different rise velocity, and also as per Prince and Blanche model, the collision model is the summation of turbulent collision rate, buoyancy driven collision rate and laminar shear collision rate. So in question 15 it is given that according to Lee et al 1987 bubble breakup model, choose the correct option. Only eddies have a length scale comparable to the bubble diameter. Only eddies which have a length scale comparable to the bubble diameter can cause the breakup. Eddies of a larger scale will give the bubble a translational velocity, both A and B or none of the above. So the answer is both A and B, because only eddies which have a length scale comparable to the bubble diameter can cause the breakup. We have seen in previous thing itself how bubble diameter which is larger than the eddies only can cause the breakup. Which was that? Yeah, they coagula and tabulates. Breakup is caused by collision of droplets with turbulent eddies. Only energy associated with eddies smaller than the bubble diameter will cause breakup. So accordingly, in this question also, only eddies which is smaller than the bubbles will cause bubble breakup. Only eddies which have a length scale comparable to bubble diameter can cause bubble breakup. This is according to Coelaglo and Tavlerites 1977 model also. And according to Lee et al 1987 model, in addition to this, eddies of a larger scale will give the bubble a translational velocity there. So both options A and B are correct. In question 16, it is given that wall effect predominates when equivalent bubble diameter is more than one third of the bed diameter, more than one sixth of the bed diameter, less than one third of the bed diameter, none of the above. This is a question similar to what we have seen in the last week. So think a minute and answer the question. So what happens is that when bubble size is very large, And the wall effect comes into picture and it plays a predominant role. We have seen that how a certain bubble diameter, after which it forms a slugging bed. So the wall effect predominates when equivalent bubble diameter is more than one third of the bed diameter. If it is more than 1/6 of bed diameter, it doesn't make any sense, and if it is less than one third diameter, again it doesn't make any sense. So the answer is one third, more than one third of the bed diameter is the right answer. In case of aggregative fluidization, bed appears to be divided into bubble phase, emulsion phase, both A and B, none of the above. We all know the answer, but again, take a minute to analyze the answer. We will discuss the answer shortly. So both A and B is the right answer because we have both the bubble phase and as well as the emulsion phase when we are dealing with the aggregative fluidization. In question 18, it is asked that the hydraulic diameter of the bed is expressed as 2E into cross-sectional area of bed available to fluidized bed by total wetted perimeter of the bed, 4 into cross-sectional area of the bed by total wetted perimeter of the bed, 2 into total wetted perimeter of the bed by cross-sectional area of the bed, 4 into total wetted perimeter of the bed by cross-sectional area of the bed. So actually basically these two are the original options and these two are the inverse options. So the answer to this one is basically, okay, sorry. We know the answer as 4 into cross-sectional area available to the fluidized bed by total wetted perimeter of the bed. So how do we define this? We know the answer is 4 into cross-sectional area available to the fluidized bed by total wetted perimeter of the bed. But I'll give you a clue actually. This is CSA by total wetted perimeter. What is area a dimension? That is meter square. What is a perimeter dimension? It is meter. Meter square by meter gives us meter. What is the unit of hydraulic diameter? It would be in meter. So in this format itself you can eliminate two of the options, that is option C and option D would get eliminated because it is giving meter by meter square, which is nothing but meter by meter square, which is giving 1 by meter. That is not the desired result. So we can, in this way we can eliminate two of the options, option C and option D would get eliminated. So these are all the questions we discussed for today's session. If you have any doubt, please ask, or else we'll close the session. We'll wait 5 minutes for the questions, and if not, we'll close the session. So, we'll just give a quick recap of today's session, and then we'll close the session since no one is there in the meeting as well. So in today's session, we saw about what are all the contents available for the pro course, and what till now we have seen till bubbling fluidized bed, and we saw about the reference books, and then we saw the unit of dissipation rate, Taylor dissipation rate, and how we found it to be the rate at which turbulence kinetic energy is getting converted into thermal internal energy. So the unit is joules per kg second, and then on converting into simpler units we obtain it as meter square per second cube. And in question 2 it was about the stabilizing the bubbles. A most important force in stabilizing the bubble, it is nothing but the surface tension force. And bubbles are much larger than the microscale of turbulence, we can neglect the viscous force. A centrifugal force disintegrates the bubble when it is keeps on increasing as the bubble size increasing. When it exceeds the surface tension force at a high pressure and high density gas, it disintegrates the bubble. So the answer is more than. Ojima et al. Model. Coalescence time is dependent on slurry concentration, as coalescence time decreases as slurry concentration increases. So the explanation is given over here. Centrifugal force is induced because of the internal circulation of the gas inside the fluidized bed, or inside the bubble, sorry, not inside the bed, inside the bubble. In question 7, it is asked that in the bubble coalescence model, the collision of 3 or more bubbles at the same time has a very small probability, and also the binary collision is normally considered. So the answer is options both A and B. Bubble coalescence occurs in the sequence as the bubbles first collide and the surface of the colliding bubbles flatten against each other, and then they trap a small amount of liquid between the colliding bubbles. So the answer is 3, 1 and 2. Option 9. According to Prince and Blanche, the collision frequency is modeled as the sum of the collision frequency from the turbulent collision rate, buoyancy driven collision rate, and laminar shear collision rate. So it is the sum of all three forces. The maximum stable bubble size as per Liu et al. Model is expressed as Dmax is 2.53 into sigma by rho Gg power 0.5. Option D is the right answer. As per Coelaglo and Tavlerites, which of the following is the correct expression for the liquid droplet coalescence rate? Tc is equal to exponential minus Tc by Ti is the right answer. The explanation is again given over here, and the unit of collision frequency between bubbles with the diameter of di and dj is given as, and the formula actually includes di plus dj square into di plus dj. So the answer is includes meter cube 1 by meter cube second, because it is the frequency, so it is meter cube second is the right answer. For the slurry column, which statement is correct? So here it is a repetitive of what we have seen in the previous thing. So bubble coalescence reduces with decreasing bubble coalescence is enhanced with in decreasing particle diameter. Bubble coalescence reduces with increasing particle diameter, or in ulta, bubble coalescence is enhanced with decreasing the particle diameter. Bubbles of different size have different rise velocities, and also according to Prince and Blanche model, bubble collision model is a summation of turbulence collision rate, buoyancy driven collision rate, and laminar shear collision rate. Both options are right. Option A and C. According to Lee et al. Bubble breakup model, only eddies which have large length scale only which have a length scale comparable to the bubble diameter can cause the breakup. True. Eddies of larger scale will give the bubble a translational velocity. Again, this is true. According to, wall effect predominates when the bubble size grows in size more than the 1/3 of the bed diameter. None of the above. More than the 1/3 of the bed diameter is the right answer. In case of aggregative fluidization, the bed appears to be divided into bubble phase and emulsion phase. Hydraulic diameter of the bed is expressed as 4 into cross-sectional area available to the bed by total wetted perimeter of the bed is the right answer. So these are all the questions for today's session. If you have any doubts, we can discuss, or else we'll close the session for today. I thank everyone for attending today's session. We'll meet again at the same time, 6 p.m. to 8 p.m. next Friday on at the same time, 6 p.m. to 8 p.m. Thanks everyone once again.